Hello and welcome to this video. We are going to be talking about, in this video we'll be talking about Lagrange's theorem. So Lagrange's, actually it's very likely going to be a series of videos in which we'll be dealing with Lagrange's theorem. So what is Lagrange's theorem? Well, Lagrange's theorem states the following. If 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 G is a finite group, right? So if all right, if G is a finite group, and so we're gonna say H is a normal subgroup of, not normal, just H is a subgroup of G. Right? Hope we know what a subgroup is. Well, a subgroup is a group, but that's a subset of the bigger group G. Right? So that's what makes H a subgroup. So if G is a finite group and H is a subgroup of G, then Lagrange's theorem says the following. Then the cardinality, or the size of G, the order of G, must divide the order of H must divide the order of G. That is, if a group is indeed finite, then every subgroup is also going to be finite. So the question is, well, if you looked at the size of the smaller group, the subgroup G, and you looked at the size of the big group G, does the smaller group divide the bigger group? So this is the claim that Lagrange is making here, that the order of every subgroup of a finite group must divide the order of the group. So our job in this series of videos is to investigate whether it is indeed true that the order of every subgroup must divide the order of the group. So how would we determine such a thing is the question. How would we determine if really the order of if the order of every subgroup must divide the order of the group? So one way to think about it is we'll say, okay, well, let's suppose, let G be a group. Alright, so this ink is too much, the brush size is too big. Let's reduce it. Let G be a group. Okay. So actually we're gonna insist that G is a finite group. So finite group. Alright, so if G is a finite group, then what has to be true? Well, one is it has finitely many elements. Alright. And let's study a given subgroup, right? One way to start is to think about, well, let's try and study a given subgroup of G. Alright, so yeah, let's study a given subgroup of G. What would the subgroup look like? And in particular, we're going to be interested in, okay, so let's say that H is a subgroup of G, and H has the elements H1, H2, H3, and so on and so forth. Alright, so this is what H consists of. H1, H2, H3. Actually, they're not infinitely many. So let's say the largest element in H is G. Has there are J elements in H. Right, so let's say H has the elements H1, H2, H3, Hg. Okay, so what in particular we're going to consider is something called a coset of H. That is, we're going to think about, suppose we got G, we got some little element G in big G, right? So we got some little element G in big G and consider GH. Right? Well, what is GH? Well, GH is just, you get every element of H and multiply it by G. So that would be, for example, G left multiply too, right? Remember, this is a group, so it matters which side you multiply by. So this would be GH1, this would be GH2, this would be GH3 right here. So the pen is really misbehaving. And then the rest will be, this would be GHJ right there. All right. Okay. So let's fix the pen. A few seconds here. Give you time to internalize the material anyway. So this pen seems to work fine. If we increase the ink flow, yeah, this looks kind of better, we hope. Okay. So this is a group, and we've multiplied every element of the group by G. Left multiplied by G. GH1, GH2, GH3, GHG. Maybe even better, like, let's actually make it pictorial. The pictorial approach might actually be better. Our brains seem to be very better primed to work with pictures, so let's work with our nature. Okay. So suppose we have, this is our group G right here. Okay, so we're gonna call this big thing our group G, and then we're gonna pick a subgroup of it. This right here we're gonna call a subgroup, subset of G that's still a group. Right? Remember, we're assuming that G is finite. So GH, right? So H would just have the elements H1, H2. Remember, it's a set, so we don't really care in what order they're written. So let's say H has the elements H1, H2, H3 up to Hj. Well, we're saying that GH would be, when we go to H, we pick some element G in G, right? We just pick some element little g in the big group G. Right? It could be an element of H, or it may not be. But here's what we're saying is GH refers to, well, what we're going to do is, let's call this GH here. If we call this GH, what we're saying is, well, we get every element of H and left multiplied by G. So now we have GH1, GH2, all the way up till GHJ. That's what GH would be. GH would be. Okay. And what do you think HG is going to be? Right? If we had to guess, what's HG going to be? Well, in this particular case, it would just mean the same thing as GH, but we're multiplying on the right. Okay, so if we drew some other box here, we're not saying that these are necessarily subgroups, so we're going to have to investigate that. But HG would refer to H1 multiplied by G, H2 multiplied by G, all the way up to Hj multiplied by G. That would be the group, that would be the set Hg. Okay. Right, so, oh, this is supposed to be G capital H. G capital H multiply elements of H on the left by GH, and on the right is multiply elements of H by G. So these things here, if we have a group, finite group G, actually in general G doesn't have to be finite, but in this case we're working with finite groups. So if G is finite, right? If G is finite and H is a subgroup of G, right, then what we're really saying is that this thing called GH, we're going to give it a name. We're going to call GH a coset. Actually, we're going to call it a left coset, which kind of makes sense, right? Why do you think we're calling it a left coset? Well, the reason we're calling it a left coset is because we're multiplying H by G, right? This is called a left coset of, we don't know if we have to need to have the of part there, but it's just a left coset of H, maybe with respect to the group G. All right. So, I mean, what questions can we come up with here? Okay, we have a coset, sure. Um, so, what's true about cosets? First of all, is a coset, is GH also a subgroup of G? Is that true? Well, what would we have to do in order to check such a detail? This is a question. Is GH a subgroup of G? Is GH a subgroup of G? Well, to check that, what would we have to do? Well, would have to show that GH, well, I mean, do we know that GH is a subset of G? Well, of course, because H is a subgroup of G. H is a subgroup of G, which means that every element in H is also in G. If we multiply every element of H by an element G by G, well, all we end up with is this, like we said before, we end up with H multiplied by all the elements of H multiplied by G's, right? But remember that H, uh, G is a group, so it's closed. That means if you multiply a group element by another group element, you still get an element of the group. So GH1 is an element of the group. It may not necessarily be an element of H, but it will definitely be an element of the group, because G is an element of the group, H1 is an element of the group, and thus GH1 is going to give us an element of the group as well. Same with GH2 and all the other elements. So one thing we know is that all the elements of GH are elements of the group. We know that. So, but if we're trying to check that GH is a subgroup, then we'd need to show that GH is closed itself. That is, if we consider any of the G1s, so for example, if we get some GI, if we get GIH, sorry, if we get GHI, right, if we get some G multiplied by HI, whatever this answer is also has to be an element. So GHI, for any I in H, right, for any HI in H, has to be an element of GH. That's what we'd have to check. But is that necessarily true? That's closure. Or even better yet, before we even think about, because I would, if this were, actually forget that. That is by definition an element of GH. So yeah, that's not really what we're worried about here. In fact, we don't even need to worry so much about, we might even need to just check a simple thing. What other property must a group satisfy? Well, a group needs to have inverses, right? So does this necessarily have inverses? Okay, so let's say we picked H, right? So remember, H has to be a subgroup of G. Well, what if we set H equals to the identity element, just one? Well, 1 is an element of G, and 1 is a group, right? Isn't it? 1 is a group, because 1 multiplied by 1, well, that gives us 1. It's closed. What's the inverse of 1? 1 is the inverse of 1. Is it associative? Sure. 1 times 1 times 1 is the same as 1 times 1 times 1, right? So it's closed, it has an identity element, namely itself, it has the inverses, namely itself. It's trivially a group. So the subgroup, if we set H equals to the identity element, then we're saying that this group here consisting of just the identity element, H equals to this, is also a subgroup of G. Now, suppose we pick some element G of G. Right? In particular, we're going to pick an element of G that's not the identity element. Right? Not equal to 1. Now the question becomes, is GH, right, the coset of G multiplied by H, where H is the identity element, does this equal to a group? Right? Is this a group? Well, what's GH going to be? It's going to be G multiplied by our set of one element, which is going to give us just what? G. Okay, so question, is G a group? Right? Because if you're trying to check if G is a subgroup, we're trying to check if GH, right, can GH be a subgroup of G? Well, to check that is, first of all, to be a subgroup, in this case, for GH to be a subgroup of G, what we'd first have to check is if G is a group, right? To be a subgroup, you have to first of all be a group. But if G is a non-identity element, and we're saying our group just contains G, how can this be a group? Because a group has to have the identity element. But our group here has only one element, which is not the identity. Right? So here we have what is called a counterexample. We found some H for which GH is not a subgroup of G. So that tells us that, sure, if we get a group, okay, this tells us if we get some group G, all right, if we get some group G, and then we take some subgroup H of the group G, okay, so let's maybe expand the space here. So, all right, so if we get some group G, and then right, get some water there. If we get some group G, and then we get some subgroup H of G, right, and then we think about GH, right, this GH, the coset, left coset GH, what we notice is that, okay, it will consist of elements of G for sure, but these elements don't necessarily form a group. They don't necessarily. That means they may form a group or they may not, but it's not a guarantee that GH is going to be a group. Actually, question, under what conditions, I mean, what would have to be true in order for GH to be a group? Or better yet, can we think of a case in which GH actually turns out to be a group? Well, let's think about that. Well, what if we start with G, okay? We start with our big G here, right? We take some subgroup H of G, right? What coset can we come up with that is definitely going to be a group? Right? That's the question. Well, we'd have to pick some G in G, and would want to ensure that GH equals to G. Sorry, GH, no, not GH equals to G, but that GH is indeed a subgroup of G, right? So our question of, well, what coset, is there a coset that is guaranteed to be a subgroup of G? That question could be rephrased as follows. Is there an element G in the group, little g element of big G in the group, such that when we take its left coset with H, what we get is always a subgroup of G. That is, so our question has shifted from finding a coset that's a subgroup of G to just finding some element of G that will definitely guarantee us that if we multiply this element with H, we always end up with a subgroup of G. Okay, so what element would that be? Let's think about this. All right, so make a guess. One thing we notice is that if we picked, let's say, if we're picking G elements of H, well, there's nothing stopping us from picking an element of H, right? So if we pick some H element of H, right? Well, if this H, right, so we pick some H over here. If we pick some H over here, over here in H, in big H, so little h in big H, well, this little h is still in the big group, it's still in the group. So that means that we can consider the coset H. That is, the element G that we pick from G turns out to also be an element of H. There's nothing stopping us from doing that. So what would we end up with? Well, we'd end up with, well, we'll get all the elements of H, let's say H1, H2, up to Hj, right? Oh, okay, so this is a little error here. So, not little, it's an error, right? No degrees of error, let's say that. Okay, so, okay, let's erase this part again. So here's really what we have. Alright, so what we're going to do is we're going to get little h times h, and what we're going to do is we're just going to multiply little h by all the elements of big H, right, of the subgroup H. So h times h1, little h times h2, little h times h3, etc., up to little h times hj. We're assuming that h1, h2, h3 up to hj are the elements of big H. Now notice, but we're saying H was picked, little h was picked to be an element of the big group, oh, sorry, of the subgroup H, right? But the subgroup is also a group, which means that H groups are closed. So H times H1 is going to give us some element of H. H times H2 is going to give us some element of H, right? Because H is an element of the group H. H2 is an element of the group H. So H times H2 is going to give us an element in our group, big H. Alright, so what we notice here is that, first of all, every element by closure of the group big H, H times H1, H times H2, H times H3, all the way to H times Hj, all of these elements are going to give us some element of big H. Okay, well, if that is true, then that means that whatever this set turns out to be, it only consists of elements of H. But the question becomes, well, sure, these elements would be elements of H, but could some of them possibly repeat? That is it possible, for example, that maybe H times H2 equals to H times H3, little h times H3? Well, that's if H2 and H3 are truly different from each other. Can this happen? What do you think? Well, let's see. Suppose that H times H2 equals to H times H3, where H2 is different from H3. That is, we're supposing that H2 does not equal to H3. Can this ever happen? Can little h times H2 equals to little h times H3? Well, notice, big H is a group, and little h and H2 and H3 are all elements of big H, right, of the group H. Which means that, well, if it's a group, they're inverses. In particular, there's an inverse for H. So if we multiply this equation here by H inverse on the left, we'd have this. H inverse times H2 equals to H inverse times H3. Okay. If we do the multiplication, we end up with, well, H inverse times H will just give us the identity. H inverse times H over here will just give us the identity. So we end up with H2 equals to H3, which turns out to be a contradiction to the fact that H2 does not equal to H3. So what does this tell us? Our original assumption that when H2 is not equal to H3, little h times H2 can equal to little h times H3 is wrong. That is, for all these separate h1, h2, h3 up to hj, h times h1 can never equal to any of the others, right? So, I mean, we just proved it for h2, h3, but it's left, please try to figure out, well, if we have some hk and let's say hm elements of h, is it where hk does not equal to hm, is it really is it possible for h times hk to equal to h times hm? Is that possible? Well, little h is obviously some element of a big group H. So you see, this demonstration will show that this can't happen, but it's up to you to investigate. It's up to us to investigate whether it can happen, let's say, when H2 and when we're dealing with HK and HM instead of just H2 and H3, right? But the end conclusion of this is really that all these elements, right, of little hh of this coset here, all the elements of the coset little h times big H are distinct. All of these elements are distinct, right? All of them are distinct, and they're all elements of H. Right. So in particular, how many elements have we got here? Right. How many elements do we have in this group? Well, the answer is as many elements as there are elements in the group H. Okay, we don't know it's a group yet. So this coset here. How many elements are in this coset? Little h, big H. Well, the elements in this coset are going to be as many elements as there are elements of H. Okay. This is important. Well, if we have as many elements as there are elements of H, okay, and none of the elements are the same, what does that tell us about this coset HG, HH? Right? Doesn't that mean that HH is really just equal to H? Okay, that's one question to ask. Is this true? Well, we have some group H, okay. We multiply every element of it by little h. The end result is we end up with h times h1, h times h2, all the way up to little h times hj. We're assuming that our group H has elements h1, h2, up to hj. Okay, how many elements are in H? Well, there are j elements in H. So the order of H equals to j. Okay. Well, now we're wondering, does little h times h always equal to big H? Where of course little h is being taken to be an element of big H. Right? Okay. Well, we noticed before that if for any k and m, right, it's never the case that if we're here assuming k and m are different, it's never the case that little h times hk equals to little h times hm, which means that each one of these h's, h times h1, little h times h2, little h times h3, all the way up to little h times hj, all of these are distinct. If they're distinct, and we have, how many elements do we have in little h times h? Well, it turns out that we have exactly j elements. So this thing here, let's say the size, the cardinality of little h times h, this coset here is is j. Okay, so we've just seen, but we said that the size of the group H was j. So we're saying that the size of this coset, little h times h, is the same as the cardinality, or the size of the subgroup H, right? The group H, right? They have the same size, and every element we saw before, every element in here, right? Because little h is an element of big H, and h1 is an element of big H. So h times h1 is an element of big H. Little h times is an element of big H. Little h2 is an element of big H. So h times h2 is also an element of big H, because H is a group. In particular, it's closed. So we're saying this coset Hg is the same size as the coset H, as the set H. It's also a coset in a sense, but it's as the set H. And in particular, every element that's in here, that's in the coset, is also an element of H. Okay, what does that tell us? Well, only one possible conclusion, isn't it? That H, the coset H times H equals to H. Right? So if in general what we're saying here is, look, why is this important? We're saying that if we have some group G, all right, and then we take some subgroup H of G, right, we could think about cosets, GH, okay? GH is just some coset, some left coset of the set. What we're saying is that, in particular, if this G actually happens to be an element of H as well, then we're saying that GH is really equal to H. That's a first realization about cosets. Okay, GH is really equal to H. Okay, and in particular, since H is a group and GH equals to H, we're saying that, well, GH is also a group then. So this is one condition under which a coset can actually turn out to be a subgroup of a group, right? Because if GH equals to H, if GH equals to H, and H is a subgroup of G, then GH is also a subgroup of G. So we found one condition under which a coset can also be a subgroup of the group. And that one condition is if the element that's creating the coset, the group element G, actually happens to be an element of the subgroup as well. A natural question to think about is, well, are there other subgroups? Is there any other condition under which, so if we have some group G, we start with our group G, we pick some subgroup of it, H, right, and then we're considering the coset GH. Are there other conditions that would guarantee that GH is a subgroup of G? That's the question. Are there any such other conditions? The one condition says that if G is an element of H, then GH is equal to H, in which case GH is going to be a subgroup of G. Okay, so of course that's a subgroup. But are there other conditions that have to, is there any other condition that would guarantee that GH is a subgroup of G? So I'm not sure about this. Well, let's see. Let's see if we can investigate and find something. If GH is a subgroup of G, right? Let's suppose that GH is a subgroup of G. Well, what does that mean? It means that, well, GH1, GH2, GHJ, this thing here, well, we're saying all these are the elements of GH, and we're saying this thing is being assumed to be a subgroup of G. Right, let's suppose that were true. Let's try and figure out what the conditions would have to be. What would have to be true about G and H? What would have to be true about this collection of elements in order for this to actually be a subgroup? Well, one thing is it would have to be closed, right? So, for instance, it would have to be true that if we picked some HK, right, GHK times GHM, right, this would have to be an element, right, because a subgroup is closed. It'll have to be an element of GH. What would that mean exactly? Well, it would mean that, what does it mean to be an element of GH? Well, all elements of GH of the form G times some H something, some H element of GH. So that means in particular that to say that right? Because if this is a group, at first it has to be closed. So GHK times GHM element of GH really means that GHK times GHM must equal to G times HI, right? Where HI is some element of H. Okay. Well, now what do we do with this information? What does this tell us about? I mean, if this is true, what can we conclude? Is the question. Well, well, I mean, we could multiply multiply both sides of this equation by G inverse, in which case we just get HK G multiplied by H little m, right? Because G inverse times G just gives us 1, so now we end up with H sub I over here. Okay, well, we can multiply both sides by HK inverse, right? Because remember, HK is an element of the group, so it has an inverse. If we multiply this equation by HK inverse, if we left multiply by HK inverse, we end up with HK inverse times HK multiplied by G times HM times HI. Sorry, all of this has to equal to HI. Oh, actually, we're missing something, right? If we multiply the above equation by HK inverse, the end result is that we now have HK inverse multiplied by HI, right? Because we're multiplying both sides by HK inverse. But HK inverse by HK just gives us the identity. So this equation reduces to G times HM. It's H subscript, so let's not let the handwriting not confuse us here. So we end up with G times H sub M equals to H sub I, right there. Okay. Now notice, well, HM is also an element of the group. So what do we do? Well, we could just multiply by an inverse again. So now we by now right multiply by the inverse of HM. So we end up with G times HM multiplied by HM inverse equals to HI multiplied by HM inverse. Right? The end result of this is HM times HM inverse gives us the identity. So now we have G equals to HI times HM inverse. Well, HM is an element of the group H. So HM inverse is also going to be an element of the group H. So really here H sub I was chosen to be an element of the group as well. So HI times HM, since H is a group, is going to give us some element H of the group. So we're saying that G actually turns out to be H sub J. Right? H sub, what letter are we going to pick? H sub L. Let's say that. That is that HI times HM inverse, while we might not know exactly what element of H is going to give us, we know it's definitely going to give us an element of H, because HM inverse is in H, HI is in H, and H is a group. So HI times HM inverse has to be, because the group is closed, HI times HM inverse has to give us an element of H. So it must give us HL in this case, where HL, we're saying HL is some element of the group H. Right, so what did we just do here? Right, let's recap. It's kind of a really long investigation. So the idea was we're trying to check under what conditions, if we have a group G and we take some subgroup H of it, and then we consider, okay, let's extend this a bit, right? And then we consider what we're trying to do here is, okay, if we get some group G and then we get some subgroup H of G, and then we think about the coset GH, which is this, right? We're wondering, well, under what conditions is GH, this coset GH, going to be a subgroup of G, right? Under what condition is that going to happen, right? Now, before we'd established that if G is an element of H, then GH is automatically a subgroup of G, right? Now let's suppose, that's what we suppose here. Suppose that GH is a subgroup of G. What would have to be true? Well, what would have to be true, for instance, is that if GH is really a subgroup of G, it means that GH is in itself a group. So it means that GH has to be closed. And we just looked here that if to say that these are the elements of GH, G times H1, G times H2, G times HJ, to say that GH is closed would mean to say that if we pick two elements of GH, namely GHK, HK is some element of H, GH sub M, right? So again, let the notation not be confusing. This is a H sub M, right here, H sub M. So H sub M is some element of H. So these two elements are elements of GH, of this coset here. And if this coset is indeed a group and is closed, then it means that this product here has to give us some element in GH. Well, what would that mean? It would mean that GHK times GHM equals to GHI, where HI is some element, right? That's what it means to be, for a product of things to be an element of, that's what it means. To be an element of the coset GH means that you have to be of the form G times some element of H. It could be H1, H2, we're not sure. That's why we're calling it HI. So GHK times GHM would have to equal to GHI. Okay, but over here we could just multiply by G inverse. So we do that, we multiply on both sides by G inverse, we end up with H sub K times G times HM equals to HI. Okay, we know that to be true. So multiply both sides to the left by HK inverse, right? If we multiply this equation by HK inverse, we end up with HK inverse times HKG times HM, blah, blah, blah. Okay. Cancelling out again, the HK inverse and the HK just give us GHM HI, right? The HK inverse on this side. Oh, did we miss something? Actually, we did. Oh, wow. Okay. So now we need to rectify this. Okay. So this is turning out to be a very fun exploration. So here's what we're going to do. Okay. So let's restate our purpose again. In this case, when it comes to the coset thing we've been thinking about right now, here's what we're saying. Suppose we have some group H. We have some group G, and we are wondering whether we've taken some subgroup H of G, and we are wondering whether GH is also a subgroup of G. Now we said that this is not necessarily true, right? Because we said, for instance, if we set G equals to the identity element, then the end result is that, so if we set H equals to the identity element, then if we pick some element G of the group where G is not the identity, the end result is that GH turns out to just be G. But how can G be a subgroup if it's not even a group, right? A group has to have an identity element, and G is not the identity. So how can this thing be a group if it doesn't even have an identity element, right? So we see that it's not necessarily true that GH is a subgroup of G. That's not always true for every G. But still we are curious. Well, are there certain conditions under which GH will always be a subgroup of G? That was the question. Before we discovered something, we said that if G is an element of H, our conclusion was that GH actually turns out to be equal to H, and since H is a subgroup of G, GH is also a subgroup of G. Alright, so we established that. If we put it in what we would say is that if G is an element of H, this implies that GH is a subgroup of G. Okay? So now let's think about the other way around. Suppose that, what if GH is a subgroup of G? Does that imply that G has to be an element of H? This is the converse of this, the other side of the implication, the converse of this implication. Is that true? Because if we can prove that this is true, the second statement is true, then we'll be able to conclude the following, that GH is a subgroup of G if and only if G is an element of H. This will be the result to be able to conclude. And if we can conclude this, we can derive a lot of interesting ideas. So, but question, is GH, if GH is a subgroup of G, does that mean that G is actually an element of H? Let's investigate that. So, suppose that GH is actually a subgroup of G, right? That's how we'd show it. We'd have to assume that GH is a subgroup of G and see if that implies that G is an element of H. Well, if GH is a subgroup of G, right, well, that means that in particular, if GH is a subgroup of G, then it means that GH is a group, which means that it's closed. So it means that if we get any two elements H sub k, any elements of the group GH, so G times H sub k, obviously HK is an element of H, and multiplied by G times H sub m, HM is an element of GH, the result we get has to give us some element of, well, if GH, we're trying to show that GH, we're saying GH is closed. So the product of any two elements in GH must give us some other element in GH. So that means that if we multiply these two things, we must get some other element of GH. But all elements of GH of the form G times some element H of the group H, big H. So let's call it GHI. Right? This has to be true for every HK, HM elements of H. GHK times GHM has to give us GHI, where HI is some element of H. Right? But if this is true, well, I mean, we know that G is an element of the group G. So it has an inverse, right? Groups have inverses. So we can multiply by J inverse. If we multiply by G inverse, the end result becomes that HK times G times HM gives us HI. Okay? We know that to be true. Sorry, actually, same mistake as before. The end result is now we have, if we multiply by G inverse on both sides, we end up with HK times G times HM equals to G inverse times G times HI. Right. But G inverse times G just gives us the identity. So we do end up indeed with HK times G times HM equals to H sub I. Okay? Well, we multiply both sides by HK inverse. To the left, we end up with G times HM equals to H sub K inverse times HI. Right? Okay. Wait. Yeah, sure. Right. And then HM also is an element of H, so it has an inverse as well. If we right multiply everything by HM inverse, we now end up with G equals to HK inverse times HI times HM inverse. Notice, HK is an element of H, so its inverse is also an element of H. Right? That's a property of groups. HI is already, by definition, an element of H. HM was an element of H, so HM inverse is also in H. So this is a product. G is a product of elements of H. Right? But H is closed. So HK inverse times HI is an element of H. And whatever result we get here multiplied by HM inverse, we also have another element of H because H is closed. So what is that saying? That this product here gives us some element in H. Okay. So we just run out of time there. So conclusion here is that G now, if this product is an element of H, then it means that G is in H. Right? So what have we just shown? We've just shown that if GH is really a subgroup of G, then G has to be an element of H. Right? So we've just shown. But before we showed that, so we've shown this part. If G is a subgroup of H, then G is an element of H. If G is an element of H, we proved that GH is a subgroup of G, which means that GH is a subgroup of G if and only if G is an element of G. Right? So that's the key takeaway from this part of our investigation, is that GH doesn't have to be a subgroup of G. Is not necessarily a subgroup, not necessarily. However, if GH is a subgroup of G, we can immediately conclude that G has to be an element of H. Otherwise said, if G is an element of H, then we know automatically that GH is a subgroup of G. All right. So we just run out of time. Let's stop here, and then in the next video we'll start from this point and continue. And remember that our overall objective is this, right? So it looks kind of long-winded, but our overall objective is this: if G is finite, if G is a finite group, we're trying to prove Lagrange's theorem. If G is finite and H is a subgroup of G, okay, we're trying to determine whether the size, the cardinality of H, the order of H, divides the order of G. And so far, to do this, our strategy so far has been, well, in order to figure out if H is a subgroup of G, sorry, if the order of H divides the order of G, we're going to think about this subgroup H, right? Because if we can learn about the subgroup H, maybe we can learn about how the size of the subgroup H is related to the size of the subgroup G, of the group G. That's our strategy. Study H and see if by studying H we can't learn something about the size of H compared with the size of G. And so far, our study of H has led us to study these things which we are calling cosets. This we're calling the left coset, and this we're calling the right coset. And so far we've concluded that indeed, right, so our whole hope of studying these cosets is that they will tell us something about the size of H compared with the size of G. And maybe we might be able to conclude that the size of H must divide the size of G, but we're not sure yet. Okay, so we'll continue this in the next episode, next video. So this was, we're going to call this episode Lagrange's Theorem 1, and the next one is going to be Lagrange's Theorem 2. Right? Investigations into Lagrange's Theorem 1, and then investigations into Lagrange's Theorem 2. All right. Thanks a lot for listening to for watching this, and yeah, have a good week, and see you in the next episode.